Hey guys, this video is for page 12 of your interactive notebook over the early atomic theories. So we're going to talk about two different atomic theorists right now who lived in very different times, and we're going to start with Democritus. Democritus was just one of several ancient Greeks who contributed to the very earliest atomic theory, and this takes place around 400 BC. Democritus and some of the other Greeks believed that matter could not be divided infinitely. So if you had a sample of matter, you could continue to divide it for a long time into a very small particle, but that eventually that matter was going to be made of small, indivisible particles that you couldn't separate anymore. And the Greek word for indivisible is atomos, and so it's from that word that we get the word atom. And furthermore, Democritus believed that these atoms would have different properties that contributed to the different properties of the matter that they made up. So on the left, we're going to look at two different examples. One is iron and the other one is salt. For both of these substances, you see that we divide them into smaller parts, and then we can divide them into even finer particles. And even those tiny particles, Democritus believed, were made up of much smaller particles, and those are atoms. But much different than the model of the atom that we have today, Democritus believed that those small atoms had an appearance that reflected the property. So for example, iron is a very strong substance. And he believed that the reason it was so strong is that the atoms were small hook-shaped particles that grasped onto each other, and that's what it made so difficult to break iron. Salt, on the other hand, you know, if you've ever actually accidentally eaten food that was overly salted, has a very sharp flavor. And so his idea for the particles that made up salt were that they were small, sharp, pointy particles, and that's what contributed the characteristic flavor of salt. So the appearance and properties of the atoms were directly responsible for the appearance and properties of the substance that they made up. Now we're going to fast forward a very long time to 1800 AD and talk about John Dalton. And John Dalton is going to expand on the work of Democritus for the first time, at least significantly, since Democritus's original idea was put forth. John Dalton was an English physicist and chemist, and we're actually going to talk about him much more later in the year. But Dalton contributed five postulates about atoms that we're going to talk about. And the first one is that all matter is made up of atoms, and this largely agrees with what Democritus said. The second postulate is that atoms are tiny, indivisible particles that cannot be created or destroyed. And this is again very much like what Democritus said. The third postulate from John Dalton is that atoms of a given element have the same properties, so the same size, same mass, same volume, etc., while they are different from atoms of different elements. And what this means is that if I had a sample of pure copper, which is an element, all of the atoms that make up that sample of copper, John Dalton would have believed that they are exactly the same. But if I was comparing the atoms of copper with atoms of aluminum,
Good afternoon, teacher.
then we would find that the copper and aluminum atoms had a different appearance from one another. The fourth postulate of John Dalton is that compounds are made up of atoms of different elements in specific ratios. So a lot of the substances on Earth are not pure elements, right? They're compounds made up of different elements of different types, and those compounds have very specific ratios. For example, water, H2O, has 2 atoms of hydrogen for every 1 atom of oxygen, and that's a definite ratio. And then the last postulate is that when chemical reactions occur, atoms are rearranged within the compound. So remember, way back up at the second postulate, we cannot create or destroy these atoms. So when we do a chemical reaction, the atoms that were part of the reactants aren't going to be destroyed, and we're not going to create new atoms, even though we're going to create new substances. Instead, those atoms are going to be rearranged, and that's how we form new products. So if we look on the left of the interactive notebook, we're actually going to look at the same two substances that we talked about above. We're going to talk about salt and iron. And when we look at iron first, iron is a pure element. So if we break that sample apart and then down to little particles and then zoom in on those little particles, we'll see that they're comprised of these microscopic solid spheres, and all of these particles are identical because they're all iron atoms. And John Dalton believed that all of those atoms would be identical to one another. Salt, on the other hand, when we break it apart, you're going to notice two different kinds of particle here. And that's because salt is not an element, it's a compound. And so we have two different types of atoms. One of those atoms are sodium atoms, and one of them are chlorine atoms. And you'll notice that all of the sodium atoms are the same, and all of the chlorine atoms are the same, but they're different from one another. But the John Dalton model is that they're still all microscopic solid spheres. You'll sometimes hear this model referred to as the billiard ball model. And so that's the end of page 12 in your interactive notebook on early atomic theories.